Let's jump right into this explainer and tackle one of the absolute biggest mysteries of the universe. What actually is gravity? I mean, we talk about it all the time, right? We literally feel it every single second of our lives. But for centuries, the greatest minds in science have been locked in this massive debate about its true nature. Are we being pulled down by some invisible rope, or is the universe itself literally bending around us?
Seriously, what is it? You drop a pen, it falls. You jump up, you come back down. But is something actually reaching up and pulling you? Or is something way more bizarre and deeply mathematical happening to the actual space around you? We're about to explore a completely incredible paradigm shift. It's classical mechanics versus a mind-bending cosmic reality. On one side, you've got Isaac Newton. He viewed gravity as a straightforward pulling force, an invisible tether between objects. But then, on the other side, you have Albert Einstein, who viewed it not as a force at all, but as the literal geometry of the universe itself. Let's unpack exactly how we got from point A to point B. Section 1. Newton's Force of Gravity, the 1687 Breakthrough. So, Sir Isaac Newton's monumental 1687 work in the Principia quite literally changed the world forever. It gave humanity our very first real mathematical grip on the cosmos. Look at this elegant equation. It basically says that the gravitational force equals the gravitational constant times the mass of two objects divided by the distance between their centers squared. In plain English, it dictates that every mass attracts every other mass instantly, based purely on how heavy they are and how close they are. And wow, was it staggeringly successful? With just this math, scientists derived Kepler's laws of planetary motion. They explained the ocean's tides. They even amazingly predicted the existence of Neptune before anyone had ever actually laid eyes on it, just by calculating these weird wobbles in Uranus's orbit. But here is the absolutely crucial point to remember. Even Newton himself was deeply uneasy about his own theory. He actually called the idea, quote, so great an absurdity. He left the actual mechanism of gravity completely unexplained because he just couldn't grasp how two unconnected masses could reach across a vacuum. I mean, think about it. How does the Earth pull on the moon with absolutely nothing connecting them? Newton gave us the math for sure, but he didn't give us the why. Moving on to section 2, where Newton breaks down glitches in the cosmic matrix. 43 arc seconds. Okay, this seemingly tiny number, it actually represents a massive cosmic glitch. As our instruments got better over time, a few tiny anomalies started to pop up that completely broke down classical Newtonian physics. We realized that Mercury's orbit precesses, which just means it shifts, by about 43 arc seconds per century more than Newton's math can possibly account for. And even when astronomers factored in the gravitational pull of every single other planet in the solar system, Newton's equations still couldn't explain this leftover wobble. It was a real head-scratcher. Furthermore, Newton's math created an impossible paradox. See, his equation required gravity to act instantaneously across any distance in the universe. But as physics advanced, we discovered a hard universal law. Absolutely nothing, not even a force, is supposed to travel faster than the speed of light. So Newton's instant gravity was literally breaking the fundamental speed limit of the universe. Not only that, it completely failed to explain why light bends near the sun, or what on Earth happens inside a black hole. That brings us to section 3, Einstein's curved spacetime, the 1915 revolution. So, to relieve this mounting tension in physics, Albert Einstein had what he famously called his happiest thought in 1907, the equivalence principle. He realized that someone in free fall doesn't actually feel their own weight. Therefore, being in a gravitational field and accelerating through empty space are locally indistinguishable from one another. This single, massive epiphany convinced him that gravity had to be built directly into the structure of spacetime, rather than just layered on top of it as some separate force. This whole paradigm shift is perfectly summarized by the physicist John Wheeler. He said, matter tells spacetime how to curve, and spacetime tells matter how to move. It's brilliant. Gravity isn't a pulling force at all. It's simply objects following the straightest possible path, which is known as a geodesic, through a warped landscape. Just imagine a heavy bowling ball resting in the middle of a trampoline, warping the fabric down. If you roll a marble past it, it's going to curve toward the heavy ball, right? But not because of some magnetic pull. It curves because the fabric itself is actually curved. 8 years later, Einstein formalized this idea into his famous field equations. Now, I know the math looks a little complex, but it's actually a really beautiful relationship. It proves that mass, energy, and momentum, which you see represented on the right side there, determine the exact shape and curvature of four-dimensional spacetime, which is over on the left side. The shape of the universe dictates the motion, and the matter dictates the shape. It's like this perfect cosmic dance. Section 4, Proof in the Cosmos, a Century of Validation. So, how do we actually know this mind-bending theory is true in the real world? It sounds incredible, but hey, science demands validation. To bring this down to Earth, let's look at something you probably use today, your GPS. Einstein's theory dictates that clocks actually run slower the deeper they are in a gravity well. Because GPS satellites are orbiting way up high above Earth, their clocks tick slightly differently than ours do down here on the ground. If engineers didn't actively correct for this gravitational time dilation, using Einstein's exact math, the uncorrected GPS in your phone would drift by about 38 microseconds a day. And get this, that tiny 38 microseconds, it equals kilometers of positioning errors. Without Einstein, your navigation app would literally have you driving straight into a lake. And looking further out, over the course of a century, Einstein's framework has perfectly predicted a series of just staggering cosmic phenomena. In 1915, it instantly solved that 43 arcsecond Mercury glitch we talked about earlier. In 1916, black holes, these regions where space-time carves so sharply that absolutely nothing escapes, were found mathematically. In 1919, Arthur Eddington's famous solar eclipse expedition proved that gravity does indeed bend light around the sun. By 1929, Hubble confirmed the universe is expanding. And then, in 2015, a full century later, LIGO directly detected gravitational waves. We're talking literal ripples in space-time caused by accelerating masses. Frame dragging, black holes, the expanding universe. General relativity absolutely nailed them all.
Let's wrap things up with Section 5, How They Fit Together, the Grand Synthesis. So does this all mean Isaac Newton was completely wrong all along? Like, should we just throw the Principia in the trash? No, absolutely not. Newton wasn't wrong, he was just incomplete. In everyday life and in weak gravitational fields, which is basically almost everywhere in our daily lives and most of our solar system, Einstein's complex equations collapse almost exactly into Newton's simpler math, which is exactly why engineers still use good old Newtonian mechanics to plot most spacecraft trajectories today. To pull this whole grand synthesis together, Newton sees gravity as a force acting instantly in a fixed absolute space and time. It's perfect for everyday physics and most standard orbits. But Einstein? He sees gravity as curved space-time, acting at the speed of light in a relative, highly dynamic universe. His framework is absolutely required for things like extreme gravity, precision timing, and truly understanding the entire cosmos. I'm going to leave you with this provocative thought as you go about traversing curved spacetime today. If the invisible force holding our feet to the ground isn't actually a force at all, but rather the very geometry of the universe itself, what else about our reality is hiding in plain sight? I really hope this explainer has shifted your perspective a bit and leaves you wanting to explore even more of these incredible cosmic mysteries.